So, going back to the model, why did we choose red as the background color for the direct feed-through blocks in the loop? Well, red should indicate danger. And to explain this danger, let us switch to another example for a short time.
You all know what's happening if you start your car while the light is turned on.
Yes,
During the starting process, the light is darker than before or after the starting process.
That's right.
If I model the battery of the car as a constant block in Simulink, either with the starter drive connected to the battery or not, the light will always see the same voltage, it has 12 volt.
Okay.
The fact that the output voltage drops if the current is flowing can be modeled by introducing an inner resistor of the source.
Okay.
Here are the corresponding Simulink models. Blue are the blocks of the ideal or the real source. Orange is the electrical behavior of the lamp. Brighter or less bright is the transformation from current to light. Please start the model, Peter. And right, we see with the ideal source, the light is brighter.
Yeah, okay.
You see a loop at the real voltage source. The challenge here is that there is no block without direct feedback to start your simulation. Such loops are called algebraic loops. The problem with such algebraic loops is that you don't know the output of the sum, as you don't know the input from the sum, the line with the minus sign. You don't know the output of Ri, as you don't know its input. And you don't know the input of Ri, as you don't know the output of 1 over R. You don't know it, as you don't know its input. This you don't know, as you don't know the output of the sum. And here you are again where you started. There are some strategies to solve such algebraic loops, but best practice is to avoid algebraic loops in complex models.
Yeah.
I still like the model of the real voltage source as it is, because it really shows what's happening. But if this is the starting point for some nitty-gritty calculations using integrators, it's better to get rid of the algebraic loop. In this simple example, this is very easy.
Yeah.
We just write down the equations of the model and solve them manually.
Nice.
In the next unit, we will deal deeper with the question how to get equations out of the model or model fitting your equations.
Sounds interesting.
The output of our voltage source U equals the open circuit voltage U0 minus the internal voltage drop Ui. Also, the output voltage equals the resistance of our lamp times the current through our lamp, R times I.
Okay.
And the internal voltage drop is the voltage that we have at the internal resistance, and this is Ri times I. Inserting the second equation into the third one yields U times Ri over R equals Ui. Inserting this result into the first equation then yields U equals U0 minus U times Ri over R,
Okay.
which can be written as U0 equals U plus U times Ri over R. And this is equal to U times 1 plus Ri over R.
Okay.
So finally we get U0 divided by 1 plus Ri over R equals the output voltage U.
Okay.
This model is much more effective. You avoided the algebraic loop. However, you don't see what's happening inside the voltage source anymore. You don't see, for example, the voltage drop at the internal resistance.
Okay.
So this was our old model of our real voltage source, and if you just can expand the model a little bit. On the bottom we have the new one, and we want now to compare the two results. So if you run the model, we see both models yield the same results, but the model at the bottom is more efficient and the model at the top is more talkative.
Okay.
You can determine how Simulink reacts once it uncovers an algebraic loop. Under simulation, update model configuration parameters. There's the tab here, algebraic loop.
In the diagnostics part on the left-hand side with the algebraic loop, okay.
And let's set it on error. What's happening now is once you try to run this model, you get here a red error message
down here, and
the loop is highlighted here, so you actually can find it.
Okay.
So, or you can just switch this to none. When Simulink tries to solve the algebraic loop in
using some internal iteration process
and without any notification, you just get your simulation results. That's all. And in between these two, there's a setting here. Warning. This means if you now run the simulation, Simulink still solves the loop, but gives you here a warning that there was an algebraic loop, so you are aware of the problem.
Okay.
Okay.
Good.